In electrical engineering and mechanical engineering, we use operational amplifiers as systems that we can analyze and use and design. So, if you haven't seen one before, I'm going to tell you a little bit about what op amps are in open loop, but this is just background information. I'm not really going to quiz you on it. It's just going to show how they work so we understand them once we use them within a system. Now, an op amp is a little device that has a positive and a negative input, and the output is going to be based off of that positive and negative input. So ideally, it's going to amplify the circuit amplify the difference, where our output would be equal to A times EB minus EA, but A is going to be a huge number, typically on the order of 10 to the 5th power, and the device isn't going to be able to output that much because it'll be limited by the power supply. So if you have a 12-volt power supply, then what that would mean is that if EB was remotely larger than EA, your output voltage would shoot straight up to 11 volts. If EA was bigger than EB, your output voltage would be about negative 11 volts, so there's some power that's lost. But essentially, unless you're working with extremely close values of your input voltages, your output is going to meet those two extremes. And that's not very useful to us, which is why we're going to use them in a closed loop system. Another thing for the specific device is that there's going to be internal resistances inside, and we're going to just assume that they're infinite because they're going to be really large. You'll learn more about that in M&I, so we won't worry too much about it here. So a closed loop circuit is one where our input and output voltage are still going to be compared with, our output voltage is still going to be a function of the difference between our input voltages, but the loop is closed in that we have some sort of feedback, possibly with any impedance Z, that kind of works as a pressure equalizer. So let's say that our input voltage EB is larger than EA, then EO is going to increase, and because you have that feedback loop, even though there might be some drop, that EA will increase as well. If EA was greater than EB, EO would decrease, which would cause EA to decrease. So what a feedback loop does is it forces EA to be equal to EB. So when we solve op-amp loop circuits, we're going to say that we have a feedback loop that forces EA to equal EB, and because of that high internal resistance I spoke about earlier, we're just going to assume that no current is flowing into the operational amplifier, because any amount that is, in order to be detected, is going to be negligible compared to the overall system, which is why we can ignore it. So let's look at an example of an inverting op-amp. And names of op-amps are not too important to me in this class, but we're going to have an op-amp where the positive terminal is just connected to ground, and the output voltage, EO, is going to flow back to the negative input across resistance 1 or resistance 2, and the input of the voltage in goes across resistance 1. So if we want to visualize this, I kind of imagine that we have two circuits here. Since there's no current that can go into the nodes, that means we can kind of split the nodes apart and just point EA and EB and say that those are going to be forced to be equal because of the op-amp. So if we have EI as our input, it's going to flow to EO across R1 and R2, and EB is going to be forced to be a certain level, and in this case, it's going to be the forced to be level EA. So we can describe everything in terms of our input current. And we go straight to the Laplace for our circuits. So our current is equal to, we always do starting minus finishing divided by the impedance between it. So we could say EI minus EB divided by R1, and that's equal to EB minus EO divided by R2. And with the other circuit, we have that EA is equal to 0 because it's connected to ground. One problem about using this example is sometimes I'll see students where they assume EA is also always equal to 0. That's not the case. It is the case for this specific example. So EB is always equal to EA, and because EA is equal to 0, EB is now equal to 0. So we can replace that top equation to EI minus 0 over R1 is equal to 0 minus EO over R2. And our output voltage over our input voltage will be equal to negative R2 over R1. And because the sign of the voltage changes, that's why this is called an inverting op-amp. Now, let's look at a second example. If you had a non-inverting op-amp, now we're going to have our input voltage be connected to the positive terminal. We're going to have some impedances in this system, and we're just going to have that the feedback loop is connected, the output voltage is connected to the negative terminal, but because we can't have any current flowing in, we also will need to set up our circuit by adding a second resistor to the ground. So you don't have to build your circuits in this class, but that's why it would be set up in this manner. So we can set up our EA and EB. Because we have an op-amp, we can visualize this as two separate circuits because there can't be any flows between the terminals. So we have one where our input voltage flows across a capacitor and then across a resistor to ground. And the other one is the input voltage is your output voltage, which can flow to ground through R2 and R3. And across resistance 1, there is a voltage drop EA. Across resistor 3, there is a voltage drop relative to ground, EB. And we can go ahead and draw some circuits in there. And so in our made-up equivalent circuits, we can say that it goes from EI to ground. And the second blue circuit, it would be EO for I2 going to ground. And we can visualize this on our op-amp by just drawing those same circuits over there. So if you don't want to draw those second sets of circuits, it's not really, it's just the way that I like to split it up, even though I know that there wouldn't be forced to be EA at that point. So it's just a visualization term that I like. But let's start talking about the currents. So we could say I1 is going to be equal to the voltage drop across. And we could say it's going to be EI minus EA over 1 over CS. I'm going to go to just simply say EI minus 0 over the total impedance. It's also equal to EA minus 0 over R1. That's going to give us less algebra if we set it up that way, but if you were to use EI minus EA over 1 over CS and EA minus 0 over R1, that would be fine. It would just give it a little bit more algebra to get to the final answer. Then we know that we're dealing with an op-amp, so we can set EA as equal to EB. So in this example, they're equal to each other, but it's going to be a non-zero number. And we can set up our final circuit. So I2 of S is going to be EO minus 0 over our total impedance, and EB minus 0 over R3. So the way that I'm going to do the algebra is, rather than solving it through and having lots that we can deal with, we can build 3 transfer functions. One that starts at EI and goes to EA, another that starts at EA and goes to EB, and a final one that will start at EB and go to EO. So we could say EO for our output over EB is going to be equal to R1 plus R3 over R3. So we get that from that equation in blue. EB over EA is just 1 because they're equal to each other. And EA over EI is equal to R1 over R1 plus 1 over CS, or R1 CS over R1 CS plus 1. Now, if we multiply these 3 transfer functions with each other, that's going to give us our overall transfer function from EO output with EI input. Because the EO over EB, the EB would cancel out with the EB over EA, and then the EA would cancel out with EA over EI, and the resulting relationship would be EO over EI. So that would get you the final answer of R2 plus R3 times R1 CS divided by R3, R1 CS plus 1. So that's our example for a non-inverting op-amp. And, you might see some other things with op-amps. There should always be a flow path that allows EB to go to ground, with the exception that sometimes you'll have a forward feed-through, which is where EO is connected to EB, and there's no impedance because EO is equal to EB, since there would be no way for a current to flow. So that's another way that you can do a circuit, but this is a nice little simple op-amp tutorial. Let me know if you have any questions.